All right. In the last class, we did charging by induction and conduction. Okay, a simple process. Before that, we learned about electric fields. So, what do you know about an electric field? Whenever there are charges around, there should be some electric field. So, if, for example, an electric field is pointing in that direction, if there is an electric field pointing in that direction, what will happen if I release a positive charge over here, like a proton? What will happen if I release a positive charge? It will go with the field. It will go with the field. What will happen if I release an electron in the field? It will go in the opposite direction. So electrons, which are negatively charged, go against the field, and positively charged particles will go with the field. Because the field direction itself is what? Field direction is the direction of flow of positive charges, right? So far you know what a positive charge is and what a negative charge is. Well, this is an important class because it gives you a complete foundation for electricity. So just pay attention and try and get as much as you can right here. So what do you know about a charge when I say it's positive? What do you mean by a positive charge? Yeah. It's having deficiency of electrons. That's simple as that, right? Positive charge means deficiency of electrons. What do you mean by a negative charge? Excess of electrons, right? Right? Keep that away. Pay attention. So you have excess electrons, deficiency of electrons, and excess of electrons if it is negatively charged. Now, how does this become positive? In other words, how does it come into existence? That's what I'm trying to explain. To bring something like this into existence, let's say we have positive charges that we can move and collect them together like this. Imagine you can have positive charges which you can group them together like this. All right? How much effort do you need to put in to bring in the first little positive charge to one place? Like, imagine there was nothing there. Imagine nothing was there and I collect a positive charge from somewhere and I bring it and put it there. How much effort is required? None. No effort required. Now, I continue that action. Go bring another little charge and I want to put it back there. Do you need to do some work? Yes. Why? Because there is a repulsion. So against the repulsion, you just push and bring it there and put it there. So you've done some work. Now I'm going to fetch the next one. I fetch the next one and I drag it. Do you need to do more work or the same amount of work? More work, because now this is building up. So the more and more this builds up, you have to put in cumulatively more and more work. Do you understand that part? And finally, I brought a lot of them and then clustered them together. I did a lot of work. All my work is going in where? It is stored. It is stored in here as what? As what kind of potential energy? Electric potential energy. So you understand the term? So we did potential energy before. We talked mainly about gravitational potential, elastic potential. Now we're talking about electrical potential. Okay? So what is stored over here is electric potential energy. Now this, what I'm talking right now, is a kind of crossover between chapter 16 and chapter 18. So chapter 17 is something that we don't do, but we need to get some foundation about that. That's why I'm flying through chapter 17. Next year, of course, you'll do chapter 17 in detail. All right, so you have a positively charged object sitting there, implies that there is energy stored in it. It's a positive amount of energy. Do you get this point clear? So this has what energy? Electrical potential energy. And how much electrical potential energy does it have? It is a cumulative effort. It's something like this. Imagine I've got a lot of bricks on the floor and I want you to kind of pile up those bricks into a wall. If I want to pile those bricks and build a wall, how much effort do you need to put in to put the first brick in place? Nothing, because it's already on the floor. So the first brick is already on the floor, no work is required. Then the first brick is already on the floor. Now, how much effort is required for you to take the second brick and put it on the first one? How much? What's the formula? FD, which is what? mgh. Remember the gravitational potential energy? So mgh, and you did the second thing. Now, how much effort do you need to put in to take the third brick and put it on top of both of them? mg2h. So fourth brick will require mg3h, and like that, the 100th brick will require mg99h, right? So you'll need to, now after you put all the 100 bricks up and build this wall, if I ask you, how much is the potential energy of this wall? It is not 100 mgh. It is 0 plus mgh plus 2 mgh plus 3 mgh. It's a cumulative thing. You add up all of them. You sum up all of them, which is what we do in calculus. We sum up all of them, and then we'll find out what is the total amount of energy that is there. The same way here. How much energy does this have? It is the cumulative effort. Now, if there's a negative charge somewhere, what is going to happen over there is how much effort is required to take a positive charge there? You don't have to take it. It will go by itself, right? It will go by itself. Why? Because this negative charge, the cluster of negative charges, has negative potential energy. So understand, electrical potential energy can be negative, can be positive, both, because you have attraction and repulsion. So negative potential energy is what this charge has. Positive potential energy is what this charge has. Does it make sense? Right? So electrical potential energy is positive here, and electrical potential energy is negative over there. Why? Because it's negative charges. Now, instead of talking about electrical potential energy itself, we define something different, which is electrical potential. What is electrical potential? Electric potential is the amount of work that needs to be done on 1 coulomb to transport it. Like, how much is the potential energy per coulomb, or work done per coulomb? The work done per coulomb, that is what we call as potential. Electric potential. We find out the work done per coulomb. So electric potential energy is all in all, the total amount of energy. But more important than that is to know how much is the work done per coulomb. Then you can figure out for everything else. This symbolically is given the symbol V. Electric potential is symbolized by the letter capital V. Work done. Work done per coulomb, per charge. So looking at the right hand side, what is the unit of electric potential? Look at that. What's the unit of electric potential? You should be able to say that. Joules per coulomb. That's what this definition says. The work done per coulomb. Joules per coulomb. This is a unit of electric potential. And V stands for voltage. So electric potential is the same thing as the voltage. And what is this measured in? Of course, joules per coulomb, but this is what we call as volt. So when you say so many volts, what you're trying to say is how many joules per coulomb. That's what it is. So try to understand the connection between joules per coulomb and volt, what it is. It's the same thing. So volt is this. So what do you mean by 1 volt? What do you mean by 1 volt? It means 1 joule required to transport 1 coulomb. That's what it means. 1 joule per coulomb. To transport one coulomb, how much energy do you need to spend? That is what it is. Now, sometimes you may need to spend energy to actually take it there, and if it is going the other way around, it will dispense that amount of energy. It will give the energy back. Like this. If a marker is sitting here, how much work should I do to take this marker and put it here? How much work? mgh. So, which point the marker has high potential? The potential energy is higher here, the potential energy is lower here. Now, gravitational potential is defined as how much work you need to do per kilogram. So, if mgh is the amount of potential energy, gh is the potential. You get it? It's per kilogram. Alright, so which place is higher potential, here or here? This is a higher potential. So to take it from below here to here, I need to do work. But when it goes from here to here, it gives out the energy. Right? Do you see it? So it depends on which way it's going. When the coulomb is going, when charges are going, when this thing is going from here to here, you need to provide the energy. When it's going from here to there, it gives the energy out in the form of kinetic energy and all the sound and heat and all those things. So you understand what is 1 volt? Clearly? So this is the high voltage, high potential. And this is at a low potential. So we say there's a potential difference between the two. There's a potential difference between the two. Sometimes symbolically we write potential difference is PD. It's the same thing. PD means potential difference. So what's a PD here? What's a PD there? It's a simple form of saying potential difference. So there is a potential here, there's a potential here. The potential difference is the difference between these two. So if this is 20 volts and that is negative 10 volts, what's the potential difference? 30 volts. Right? If this is plus 20, that's minus 20, potential difference is plus 30. Yeah.
Why does the positive charge have high potential?
Why does higher potential? Because you need to do work to transport coulombs to there. Why this one has negative potential? Because to transport a coulomb, you don't have to do work, it will do the work by itself.
So like doing work, you're like giving potential.
Yes. When you do work, you give it energy. When it does work, it loses its energy. When someone does work for you, you gain. When you do work for somebody, you lose. Right? You have to. When someone does your work for you, you stand to gain. And when you do work for someone, you stand to lose. You lose calories, you lose money, so many things. Okay, so that's basically what it is. So why this is positive, higher potential, and why this is lower potential? Because over here, the charges will go, the coulombs will run to it by itself. You don't have to take it. And therefore, it leads to a lower potential. All right, now, what I'm putting over here on the board is just a very shortcut way of leading you from chapter 16 to chapter 18. It is not a complete learning of potentials. We will learn it in detail next year, properly. But right now you understand, so all I need you to understand is, what is the so-called volt? It is 1 joule per coulomb. That's the meaning of volt. Correct? So, when there is a potential difference from one place to another place, there is a chance for something to go from one place to another place. When there's a potential difference between these two levels, there's a chance for something to go, if allowed. If allowed, there's a chance, right? The same way you can see the connection of the same concept in different areas, and I'm going to lead you to different points. Here is a tank of water. That's a full tank of water. And this, oops, that's an empty tank. I was almost going to say, it's a tank. No, it's an empty tank of water. Almost going to say that. All right. That is an empty tank, and that is a full tank. When you connect these two by a tube, if you connect it by a tubing, what will happen in here? Water will flow. Why should water flow? Why is water flowing from one place to another place? Why is the water flowing from here to there? Pressure difference, exactly. It's a pressure difference. Outside is atmospheric pressure, and behind here is water pressure built up somewhere. So there is high pressure here. There is a lower pressure here. What makes a fluid move is the pressure difference. Now you can talk about water moving like this or air. Why should there be wind? Why is the wind going from here to here? It's because of pressure difference. So if you look at a weather map, you will see pressure is high and pressure is low, so the wind is actually this way. The wind has to go from high pressure to low pressure. Now what creates a high pressure and low pressures and all that? Temperature changes and multiple factors. There are multiple factors which makes the pressure change. And depending on the pressure, now if you don't see any wind outside at all, that means in your neighborhood there is hardly any pressure difference anywhere. Right? That's why it's like still. Alright, so what makes the water flow is the pressure difference. And so what you see inside here is a water current. Don't you say water current when you actually look at water flowing through a river and all that? Don't you use the word current? Yeah. Like you'll be standing next to a stream and you'll say, oh, the current is too much. Use the term. What is current there? You're talking about the flow rate. The rate of flow is too high. That's what you're trying to say. And when the rate of flow is too high, a lot of fluid is moving per second. So we can call it water current. So when you have a high pressure here and low pressure here, the water current is going to be pretty good. Can this water current do useful work for you? Can you put this water current to do something good for you? Yes, Dad. Hydraulic. So, okay, so what I can do is I can put a turbine right there. You know what a turbine is? So when water gushes through the turbine will spin, and I can connect the turbine axle to a fan blade. So what happens is the turbine is connected to a fan, so when the water starts gushing through this thing, the fan will start spinning and breeze me. So as soon as I open the water through this thing, the fan will start working. Now my question, is the fan going to work continuously, forever? Why? Yeah, once the pressure is equalized, there's no flow. So what happens here is this level is going to come down and this is going to go up. When these two levels match up, there is no pressure difference. And when there's no pressure difference, there's no current. Do you understand this concept? When there's no pressure difference, there's no current. And when there's no current, this turbine is not going to spin, therefore the fan will stop breezing me. So, how can you get continuous current? Tell me a method here whereby I can have this fan spinning continuously. What should you do? So how do you do it? Tell me practical. Yeah.
You can set up one of those vacuum tubes that goes into that tank, and you can really quickly put it into the other tank and then seal it so that it's constantly sucking water out of everything.
So, like for example, the water is coming from here. You need to throw the water away, right? So, can I do this? Just asking. Can I do this? I can just take this and dump it there. So as soon as you open the thing, water comes from here and it exits from here and then gets dumped. Is it okay? If not okay, tell me a justification as to why.
Wait a second, because the water would have to be higher pressure.
Say it again.
It has to be higher pressure.
It doesn't have the energy to go up. Any other opinions? Like my question is, the water is going to come freely here. Why can't that water go from here and then get poured out there so that this will go on and on and on forever? That'd be a wonderful machine. All you do is just pour water here and then connect it up and you can get fan breezing all the time. So definitely it's not going to work. Tell me why it won't work. Yes, Graham.
Is it because the pressure at the end of it would like be higher?
Here?
Yeah, it would be like higher there than it was.
Isn't the pressure higher here than here?
No, it'd be higher.
As you go down in the fluid, the pressure should go high. It's. I know you are almost striking the answer, but you're not able to get it out. Yes.
The pressure would like equalize halfway through the tube. So a lot of it's not good.
Pressure equalizes halfway through the tube.
Yeah, like it wouldn't.
Like here?
Yeah, like. The
If I practically do this, what will be the consequence? What will be seen?
it'll just be the tube.
Yeah.
Will the tube fill up with water all the way up to the water level?
Exactly. That's what's going to happen. The water will actually come all the way here and will come up here. By the time this much, a little water will come off. So once it comes to that height, there's no chance of it going up because for the water to go up, you need extra pressure. Once it comes to the same level, it can't go up higher here. If you want to make it go higher, you need to push it somehow. So you need a pump. So if you want to go make something go higher than its normal level, you have to put a pump or something like that. Otherwise, it will seek its own level. The water will come out from there and come to this point, and that's it. Stop. So the water current is going to be zero after that. Because when the water level in this tube comes to that height, the pressure that it creates over here is the same as the pressure created by this water right there. You'll learn that next year when fluids. But right now you can understand that it's not going to work. So this is definitely not going to work. So what's the remedy? What is the remedy for continuous current here? You want continuous water current. What's the remedy? Yes.
You use the power that the turbine creates to flow back out.
So in other words, he's saying like use this power that this one creates to run a pump. And the pump will actually push that up inside. Again, that leads to perpetual motion machine, which is not possible. Because energy is conserved. You can't generate as much energy to produce more energy than what is being there. So you cannot just create more energy, simple as that. Yeah, technique is, he is thinking of a technique that's good. Like this is already getting powered, so use that power to power a pump. But then understand, the power that you have is supposed to be divided. So energy is conserved, so energy cannot be, the end product energy cannot be more than what you had before. It can only be, yes.
Add more turbines, more energy.
I'll add more turbines here.
Yes.
In fact, that is one thing you should understand. If you add more and more turbines, you're restricting the flow rate completely. Have you seen those wind turbines? How many blades do they have? 3. And that too very narrow. Why can't they just fill it up with 20 blades? And then it'll stop the whole flow. So which means it won't spin. So you can't just fill it up with blades all over the place because then it won't spin. Because you need to let it spin and you need the flow continuously going on. So if you just fill it up with blades, it will block the flow, which once you block the flow, it is not going to spin. Yeah.
So like huge field, like wouldn't it restrict some of them from spinning?
Which one? You're talking about the wind turbines?
Yeah.
What fields?
Like up north, there's like huge fields, like with like hundreds of them.
Oh yeah, but
Doesn't that stop those?
no, but look at the empty places here. And plus, they won't keep one behind the other. There's always a kind of, the placement is not always like one behind the other. Even if it is one behind the other, they are far apart. They look like as if they're close by, but they're far apart. So the flow is not really affected by the blades. How much volume do those blades occupy? If you look at the whole thing, it's just negligible. Yeah.
Did you know that like throughout like their like lifespan or whatever you call it,
not a living thing, but throughout like the time that they're like producing energy, they won't produce as much as it took to install them and put them where they were. Like if you look into all
You mean
the
the cost-wise?
um,
Like cost-wise, you're saying it's not worth it.
I think it's I can't remember if it's cost wise or if it's like actual like energy used to get them there, like overall looking at like producing each part and all that to like actually put it into place.
I doubt it. I mean, it is definitely useful because once installed, it is just an electromagnetic generator, and it should keep working forever. There's no lifetime for that. You know, if you just like I think yes, the initial cost is high, but all those things are connected by a grid. They're all connected by a grid, and so yes, it is an expensive thing altogether. But then eventually you're getting a power grid system. Yeah. Yep.
What's the most efficient natural energy? Like water, sun, air.
Natural, it depends on how you tap that energy. Now, water is pretty strong because you're having hydroelectric power stations. They just work because the water levels. That's it. Water coming down, turning the turbines. That's how we are all getting most of our energy. Hydroelectric. The energy that we get here is by burning coal. So LG&E burns coal and then converts water to steam, and the steam will turn the turbines, and the turbines will turn the generator, and then we're getting electricity. So we are doing that. In the Middle East, they burn gas because they have plenty of gas. They just connect the pipeline straight away, and then it produces an electrical energy. So different places use, and nuclear method also is used for generating electricity, so which is more efficient. Electricity is the most efficient form of energy for transfer. If you want to transport energy from here to Lexington, electrical energy is the best form. You can transport electricity from one place to another place with the least loss. Least loss. You can't transport any other form of energy that effectively. Okay? And that's why electricity is on top. That's why most of the energy production leads to electricity, because then you can transport it wherever you want. Yeah.
Keep on adding water to the one on the left.
Yes, you keep on adding water. Who's going to add that water? I mean, if you're going to use a pipeline, if you're going to put a pipe over here, if you're going to put a tap over here, then what's going to happen is you're going to waste so much water just to make this fan spin. So somebody has to do the work for you, right? Now, where's the water coming from? The water is coming from the tank, and the tank is getting emptied, and somebody has to pump that water up, and then you pay for that. Yeah.
Different way to tilt it each time, like when you even down, you tilt it one way so it flows, and then you tilt the other way.
That's. But who's going to tilt it? Now, to tilt it, you need to do work. To tilt it, you need to do work, because once this is heavy.
What if you had like a balance, where it's balanced, but one side filled up and way enough to tilt it to the other way?
It goes the opposite way. It should go the opposite way. Yeah, gravity. I mean, if this is getting heavy, it goes like this, but you wanted to go the other way around, so you have to go and push it. One way I can do it myself is to use my energy, my calories. So I stand under this, and I take this jug over here or mug over here and fill this up and empty it there, and fill this up and empty it there. I just physically dump the water that's coming from here into that, which means I am inputting the energy. The energy that I spend taking the water from here and dumping it there is what makes this one work, and the fan will breeze me because I'm doing the work. When I become lazy and I do less work, the fan will slow down. The more efficiently you do the job, the more it will do for you. But again, there are losses even there. So all my energy is not going to the creation of this. Okay? So you understand the main idea here. What drives this water current? Pressure difference. Make sense? Pressure difference is what takes the water here. And if you can maintain this always excess of water, and if you can always maintain this deficiency of water, you can actually have this water current continuously going on. And you can use that water current to do useful work for you, like spinning a turbine. Now we are just bringing it, the same idea, to this. That's a positive charge. That's a negative charge. The positive charge has high potential energy, right? This is positive potential. This is negative potential. So just as there was a pressure difference from here to here, there is what? A potential difference. There is a potential difference between these two. Yeah, there is a potential difference, but it will not do anything unless you let it go. To let this charge go, you need to connect it. So to connect it, you can connect it not by a pipe, basically by means of a copper wire. So you just take a wire and connect it. So if you connect a wire across the two, now copper. What is special about copper?
It's a conductor.
It's a good conductor. What about this material? What about material? What about this? Can I connect this across? Does this have electrons? Yes, but they're not free to go. They're all bound. There are no free electrons. Whereas in copper, there are lots of free electrons. So there are a lot of electrons already. Look, that copper is already filled with a lot of free electrons, ready to go. What happens as soon as you connect the copper wire across the two? This is deficient of electrons, so it wants electrons. So what will happen to these electrons? It will start pulling up. So these electrons will start drifting this way. The electrons will start drifting this way, creating an electron current. Which way is the electron current? That way. Now, the water current was this way, from high to low. But the electron current is from low to high. Why is this going this way? Because they are negatively charged. Negatively charged, they go in the opposite direction. Positively charged ones should have gone that way, right? If there were positive charges that could move, then it would have gone that way. Just like the water. That's why even though the electron current is in this direction, we call conventional current that way. So electron current is completely opposite of the conventional current. Conventional current means what? That is how everything works. Everything goes from high to low. Since everything is going from high to low, see, this is going from high to low. Everything is going from high to low. And therefore, why do we consider this to be the actual current direction? Let's consider this to be the current direction. And so what is the conventional current defined as? Is direction of conventional current is defined as the direction of flow of positive charges, or opposite to electrons charges. So conventional direction of current is taken as the direction of flow of positive charges. So when you say current in electricity, this is what we talk about. The direction of flow of positive charges. The conventional current is symbolized by the letter I. Conventional current is symbolized by the letter I. So what is I defined as? What is water current defined as? The amount of water per second. The volume of water per second. That is what water current is. The same way here. The conventional current, I, is defined as the charge per second. Charge flowing per unit time. Rate of flow of charges. Rate of flow of charges. Rate of flow of charges. So I is equal to Q over T. I is Q over T. I is Q over T. What is Q measured in? Coulombs per second. What is I measured in? Yeah, what is the I measured? What's the SI unit? What's the basic unit of current? Amperes. So amperes is coulombs per second. So ampere is coulombs per second. That is a unit. The equation for current is this. So when you say 1 ampere, what does that mean? 1 ampere means 1 coulomb per second. It's a big current. 1 ampere is a big current. 1 coulomb per second. How many electrons is that? 1 coulomb is how many electrons? 6.25 10 power 18 electrons. So if 6.25 times 10 power 18 electrons cross a certain spot per second, then the current is 1 ampere. So you understand the connections there. That is called 1 ampere. Now, is this conventional current flow, the flow, is it a constant? Is that going to stay constant? Is it going to stay a constant? No. So as soon as electrons come here, this becomes less positive. That means less deficient. And this becomes less negative. Right? This becomes less negative because electrons are drawn from there. And electrons are arriving here, which means that makes it less positive. So eventually they will just turn out to be the same potentials. And what will happen to the current then? Stops. The current will completely come to a halt when the potentials are exactly the same. So if I have 1,000 volt over here and 1,000 volt over here, exactly 1,000 each, I can touch 1,000, and I should be perfectly okay. I should be perfectly okay when I'm 1,000. I'll be at 1,000 volts potential, but there is no potential difference. You know what I'm saying? If there's a potential difference, that's when you have a possibility of a current. If there's no potential difference, no chance of current. I remember a time when I was in grade 8. I was interested in electricity, as you all know. I was interested in knowing many things. So I wanted to know if I know that a potential difference is what is needed to make a current flow through. So I was just thinking to myself, I said, if I take a wire from the live terminal and put it on the bed, on the mattress, and the mattress is insulated and is on a wooden bed and is definitely not connected to the ground at all. So if I throw the wire on top of that and if I hop onto that bed and if I touch that wire, will I get a shock? Look at my curiosity when I was in 8th grade. But I was not daring to do it because my parents will scold me. So therefore, I was waiting for a time when they will not be there at home, like when they go to church or something. I said, nobody's at home now. Best time to do some experiments. And I just plug in a wire. I actually did this. I plugged a wire there and put it on the bed. And I got on top of the bed and I held the wire like this and I said, okay, now I have to touch it. Technically, well, this is 220 volts. In India, it's 220 volts. I was looking at that and okay, if I touch that, I should not get a shock, theoretically. Now, is that okay to go and touch it or not? I was like scared first, so I just didn't want to touch it straight away. So I just went flying above the wire and trying to touch it on the fly. You know what I'm saying? I don't want to go and touch it like that. Instead of that, I miss many times. Because when it goes nearby, I'm just kind of scooping over it. So I just finally, I just touched it. I said, yeah, I touched it. And I slowed down the touching. Slowed down, and I didn't feel anything. Slowed down, and finally, Nothing's wrong. I was holding it, and I said, okay. Then I started suspecting maybe that wire is not plugged in properly. Maybe that wire is not plugged in properly, so probably it is loose or something. Maybe there's nothing here. And that's when my brother walks in. He was in grade 5. He walks in, and I told him, go and fetch that tester. There's a tester with you put the finger on top. Like, for example, if something is live, it's like a screwdriver. You touch the metal end to the place where you want to test, and you put your finger on top there. So the tester bulb will come on. Because it's a neon bulb, it actually will light up to let you know that it is live. So I know where it was kept, so I told my brother, I bring that tester. Don't touch me, just come close. So he came close with the tester, and I said, put your finger, because I have to teach him how to use it. So I put a finger there, and then come close, and I just held this wire, and I just stretched out, and I said, test my hands. So he put the tester on my body, and the thing was coming on. That light was lit. Wherever it was, wherever he touched, that light was lit. Meaning what? Meaning my whole body was 220 volts. But there was no other reference for the electric current to flow. And that's why nothing was happening. I didn't feel anything at all about it. You understand what I'm saying? Now, if accidentally, if I had touched my brother also, and because he was on the floor, we both would have got killed. Because it is 220 volts, not to play with that, but it was something like dangerous. But I knew what not to do and what to do and all that. So I tested it, and I knew that okay, that is plugged in properly, and I'm absolutely okay. I'm not having any. Now, that's an experiment that I did long back. Of course, I've got my share of shocks plenty of times, but that was an experiment which actually kind of taught me. So thinking of the birds sitting on those high tension wires, high tension wires like 440,000 volts. The birds are coolly flying and sitting on top, and you think like nothing is happening to it because there's no potential difference. That's why. If there's no potential difference, there's nothing wrong. You get it? Yeah. That's a good concept also to understand. There is a potential difference between this feed and this feed, but it's tiny difference, very tiny, compared to 440,000 volts on which it's sitting. There's nothing there. So how can you make this thing flow continuously? How did you make this flow continuously? Because as soon as the water comes here, you have to take that and put it there, right? And if that can be done, then it will go on forever. Same thing here. These electrons are arriving here. You don't want this to lose its potential, high potential level. So what do you have to do? Take those electrons as soon as they arrive here and dump it there. Take these electrons, dump it there. And if you can do that, with so many electrons, then you can make this current continuously do this. You understand what I'm saying? Now, if you can do that, then that is what creates a continuous flow of current. This is what is naturally done. Okay, can you see this bud over here? That's a positive potential. This thing is a negative potential. How many volts is this? What's the potential difference from here to here? How many volts? You should know this. Because you use your calculators, you put these things into your calculators, like the little ones. You put triple A's. How many? Read what is written on the cells. Take your calculators, take one of the cells out, read what is written on it. Read. Rechargeable will be smaller, but 1.5. Rechargeable will be 1.2. If you have rechargeable, is it pull-out rechargeable or not? Oh, it's inbuilt. Okay. So if it is a pull-out rechargeable ones, it will be 1.2 volts. But these things are, the alkaline cells are 1.5 volts. This is also 1.5, so you can see it written down here. It will be written 1.5, and you can also see a plus sign written right there. You can see a plus sign on the top, which is basically telling you that this is deficient of electrons, and this is excess of electrons. But what exactly is happening inside here is this is excess of deficiency of electrons, and this is excess of electrons. If I connect a wire from here to here, Electrons are going to run from here to here, correct? But the electrons are going to run for a long time. How is this working? Somebody has to take these electrons and put it on the other side. And that is done by a chemical reaction. That's why we have an electrolyte inside here. So what's inside this dry cell? What's inside this cell is this. It has a container made of zinc. So the bottom of this thing that you see here is a zinc container. And this is a zinc container, and the top part of it, this is a positive terminal. That's a positive terminal, which is connected to a carbon rod. So this is a carbon rod. And this carbon rod is in an electrolyte, and this electrolyte is ammonium chloride. That is ammonium chloride in jelly form. Like jello. That's how it is inside. So if you happen to open it, you'll see the ammonium chloride jelly. Of course, it's added with other stuff like manganese dioxide and all those for removing oxidation things. But anyway, the main things are, there's a carbon rod, there is zinc, ammonium chloride, cell. You want to create a cell your own? Yep. Take a glass container, put a zinc rod in it, zinc wire, put a carbon rod into it, just a carbon, and there it is, positive, negative, and put ammonium chloride inside. Just ammonium liquid. Just pour ammonium chloride liquid inside here, zinc and carbon, you have a cell. So that's basic. Now this is more compact because it's in a jelly form, so it won't leak. But if you release it, if you let it go, stay there for a long time, there can be some corrosions and all that, and then slowly the gel, the ammonium chloride will start leaking out, and it can really cause a lot of mess. Have you seen that mess? Ammonium chloride comes out, and then after that all those springs get really corroded, and it damages the whole thing. That's why they say don't leave your cells inside your remote controls and other things which you're not using regularly. Take it away, keep it aside, put them only when you want it. If you leave it there forever, it will eventually, so not all of them will leak. Some of them will leak because of the extra corrosion of them. So what is maintaining the potential difference here is the chemical reaction. And the chemical reaction will take place only when it is needed. Only when needed. Only when I use it. Only when I use it. Only when I connect a wire, then only the chemical reaction comes in. Otherwise, the chemical reaction doesn't have to start off. So right now it is idle. 1.5 volt is ready for you to use. You can use it anytime. How many volts is coming out of that socket? You plug so many things inside there, you should know what's going on. Huh? How many volts in that socket? Oh, there's not, you can't read it. I don't think it's written. I don't think it's written. I don't think it's written. I don't know if sockets have that written down, but anyway, you can try it. 220 in India. It is 110. So over here, we have voltages which is 110 minimum. It should go up to 120 max. So it's basically 110. We call it 110 volts. How many volts is this? What do you mean by 1.5 volt? Tell me what is the meaning of this. It means that when you want to take, when I connect a wire from here to here, to transfer 1 coulomb from here to here, how many joules required? 1.5, 1.5 joules. That's why it's 1.5 volts. Now if I connect a wire from one hole to the other hole there, it's 110 volts. So for transfer of 1 coulomb across, how many joules of energy is dissipated? 110. Now if I hold it like this, is there a current flowing through my fingers? I'm holding it like this. Is there a current flowing through my fingers? Yes. There is a current flowing through my fingers. Which way? Which direction? Tell me which finger to which finger? Current. Current is flowing from positive to negative. But which way are the negative charges going? Remember, my body here has a fluid inside which is made up of ions. So it can have negative ions and positive ions. The negative ions are going to go this way, and the positive ions are going to go this way. Yes, there is a current in my fingers right now, but I don't sense it. It is too small. So even if I attach to Lucas, he won't get anything at all. Right, Lucas? Okay. So when you touch it like this, nothing happens. Now what if you go touch the car battery? How many volts is the car battery?
2.
2. Car battery, how many volts?
Car battery.
The regular car battery. Now, these are numbers that you should know, at least for general knowledge purposes. It's 12 volts. It's 12 volts. So what will happen if I touch the positive and the negative leads together? What will happen? Huh? Yes, my body. That's a positive terminal, that's a negative terminal. I just go bare hand, positive, negative. What will happen to my body? Nothing. Nothing. It's only 12 volts. 12 volts is not going to cause anything at all. Yes, there is a current, but it is not big enough to interfere with the current generated by the brain. You know, your brain actually sends electrical impulses to all your muscles. It's an amazing thing. Look, if I want to lift this cell from here, first the brain gets a command saying, all right, your intention is to lift this thing. So immediately the brain releases those electrical pulses to the required muscles to lift the hand. How is a muscle lifting? It's because of an electrical impulse generated from the brain. You understand? So the brain sends the required signals to these muscles to make my muscles move so I can lift my hand intentionally. And then now it goes there and I'm going to hold it. Now when I'm holding it, the brain is telling the muscles in my fingers to now contract, hold it, grip it, now lift it. All these signals are given by the brain and you don't have any idea what's going on. Everything is controlled by the brain in terms of signals, electrical signals. Yeah.
So does that mean you're just like sending shocks to your muscles to make them twitch?
Yes. Through this. But it's a smaller current. It's not too big. So they're all electrically motivated, electrically triggered. You can actually, like, if you take a chicken leg, stick one terminal on one side of the muscle of the chicken leg and stick on the other side another wire and give electricity to the chicken leg, you'll find the chicken leg like moving. Seriously. The chicken leg will be acting as if it's alive right in front of you. Right? It's a dead leg. It's not supposed to move, but when you electrically just connect something, it will move. That's exactly what happens to us too. Pay attention. So what is happening is, when I touch somewhere, I will get a shock. But the shock is probably not big a shock, and so I understand what's going on. Now, how many volts is this battery? 9 volt. Now, 9 volt is pretty close to 12. That's 9 volts. And if I connect a multimeter over here, it will show 9 volts. But if I don't have a multimeter, the quick way to check if it's got some juice in it, by licking at it. So just touch it. See, I'm touching on the tongue, both the terminals, and I feel like it's sour. So I feel like something is really sour on my tongue. What is happening there? There's a current flowing, there are ions flowing on my tongue, releasing little bubbles of gases right there, and that is what you feel. So there's a little electric current passing on your tongue. Anything wrong? Nothing wrong, because your brain is still in control. The brain understands that you're getting a shock. So what current will actually cause you to lose control? So if I'm going to touch something like 50, 60 volts, you can enjoy that. If you touch 50, 60 volts, you can feel a rubbery feeling, a tingling feeling, and your brain will tell you you're getting a, you're feeling an electric shock. But the brain has full control still, and therefore you can enjoy that. You feel the shock and you can enjoy that. But if it goes a little beyond that, what will happen is the muscles, your brain is telling the muscles to stay there, but the electric current that you are pushing through is telling it to fly away. So you touch it and your hand flies away. Why? Not because the brain told you to take it away. It is an electrical impulse. The muscle twitches. And as you're taking your hand, you may hit your neighbor's face also. But all this is not intentional. It's not like intentional. Like when you get a shock, your brain doesn't say, you're getting a shock, take your hands off. Now, it doesn't happen that way. It is the other way around. When you get a shock, your hand flies away, and then your brain tells you, you just got a shock. Okay, it's the other way around. So yes, electrical current of, when the voltage is 60, 70, you get a shock. I can take 90 without having any problems at all. But more than that, it becomes a little hard to handle. Yeah.